Alright, hey guys, I just recorded this video, but unfortunately the audio did not work, so I have to record it for a second time. Anywho, who cares? Let's just go on to the problem. Whatever the species of butterfly has ZW sex determination. The wing spots are normally orange, but a recessive Z-linked mutation causes the spots to be yellow, while a recessive autosomal mutation causes the spots to be red. Butterflies homozygous or hemizygous for both mutations have no wing spots. What are the expected F1 phenotypes from a cross between a true breeding yellow-spotted female and a true breeding red-spotted male? Right off the bat, for this species of butterflies, they do not follow the typical XY chromosome sex determination. They follow the ZW sex determination. And what that means is a female has the genotype ZW, whereas a male has the genotype for ZZ. We have a recessive Z-linked mutation, which causes spots to be yellow. So we have two genes located on the Z chromosome. We have the regular Z, which is dominant, and it produces an orange color. We have ZY, which produces a yellow color, and it is recessive. So let's say we had a male. Let's say he has ZY as a genotype. What that means is the phenotype he will express is an orange color, because he has at least one Z that does not have a mutation and has the dominant orange color. If we had a female, on the other hand, that had ZW, she would produce, likewise, an orange color, because she has an allele at the Z chromosome that will produce an orange pigment. If she had ZYW, she'll produce yellow spots, because she only has one Z chromosome. So whatever chromosome she has with whatever allele it contains is going to be expressed. In this problem, we know that there is also a recessive autosomal mutation that causes the spots to be red. So here's the key word: recessive autosomal mutation. Let's ignore the recessive part for now and just focus on the autosomal mutation portion. Autosomal mutation means that it's a mutation located on any chromosome apart from the sex chromosome. Autosomal is going to be located on an autosome. An autosome is any chromosome apart from sex chromosomes. So right off the bat, we know that we have a recessive autosomal mutation as well. Since it's autosomal, we know it's not going to be located on the sex chromosomes. It's going to be located on some different chromosomes. So we're going to have an entirely different chromosome with entirely different genes on it. So we're going to let's say we have big R and little r. Big R produces no color. Oh no, big R produces, no pigment. Whereas little r is going to produce red spots. And again, since this is an autosomal mutation, it's not going to be located on either a Z or a W chromosome, because those are sex chromosomes. So if an individual, for example, or out of what it says right here, butterflies homozygous or hemizygous for both mutations have no wing spots. So if we had an individual, let's say it was a male, and he had ZZ, which would normally produce an orange phenotype, paired with two homozygous recessive mutations at the R gene, we would have an individual that produces red spots. Now, if we had an individual who was ZY, little r, what do you think it produced? The answer to that would be red spots. It says right here that butterflies homozygous or hemizygous for both mutations have no wing spots. So we know that this individual has a Z and a ZY. The ZY is recessive, and it's going to be masked by the effects of the dominant Z gene. So this allele is going to mask the effects of the yellow recessive mutation. So it's going to produce an orange color. So the red spots is going to have an impact on that color. So instead of producing orange spots, it's going to produce red spots. Now, if we had an individual who was homozygous recessive at the Z locus, ZY, little r, then we would have no spots. This right here says, or hemizygous. Hemizygous means that it has at least one of those alleles. And we know that females can only have ZW. So hemizygous, that pattern, only occurs for the female in this case. For a female, if she was ZW, little r, she would produce red spots because she has a working Z gene for the orange spot color, and that's going to be affected by the little r's. Whereas if she was ZYW, little r, she's going to have no spots. She's hemizygous, this mutation. Since she only has one Z, it's going to be impacted by the r's. So now we have that down. Going on to the question, what are the expected F1 phenotypes from a cross between a true breeding yellow-spotted female and a true breeding red-spotted male? So a true breeding yellow-spotted female. So true breeding means that this individual is going to pass on the same genes for its phenotype to its offsprings. So it's going to be homozygous, either dominant or recessive at the locus. So we have a true breeding yellow-spotted female. She's going to have the genotype ZYW, and we know she's true breeding, meaning she's going to be homozygous, dominant or recessive. And we have the other locus we have to look in, the R locus. Now, since she's yellow-spotted, we know that the R locus, or the alleles there, did not have an impact on the phenotype, which means that they are both homozygous dominant. A true breeding red-spotted male would mean that this individual has 2 dominant Z's and 2 recessive R's. So if we were going to try to find out the different phenotypes that can be produced, we'd have to do a cross for both of the genes. So right now, let's do a cross for both the genes, Z and the R. For both individuals, we'll have the female on top, ZYW, male on the side. Now we're going to do the same for the R locus. And it doesn't really matter what side you decide to put the males or the females on. You could put it on either side. You could put the male on top, the female on the side. It doesn't matter. I'm just going to put it on the side because I feel like it. Alright, so we have 2 out of 4 of them being females, 2 out of 4 of them being males, and we know that for the males they have Z, ZY. They have 1 dominant Z, so that is going to express an orange color. So 2 out of 4 of the males, or all of the males, are going to be orange. Now, we have to look at the R gene, or at the R locus. 4 out of 4 of them, or all of them, are heterozygous, meaning they have at least 1 dominant allele and 1 recessive allele. So, the effects of the recessive allele are not going to show on the organism, which means that all the males are going to end up being orange, even after we look at this, at the R locus. Likewise, if you look at the females have 1 dominant Z, so they're going to be orange. So we know that all males and females of the F1 are going to be orange. Going on to question 2 of the problem. The F1 individuals from the cross above are mated to each other. Write down the expected F2 phenotype frequencies out of the total progeny and enter these expectations to answer the following questions. What is the expected frequency of orange spotted males? Alright, so now we're going to have to try to cross the F1s and get the F2. So we're going to take an individual, a male from the F1. He's going to be Z, ZY, and we're going to cross that with a female from the F1 and she's going to be ZW. So we get Z, 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 ZY, ZW, ZYW, and that gives us 4 different genotypes. Now we also have to do the same for the R locus. All the individuals have a heterozygous, have the heterozygous genotype at the R locus, so it's going to be big R, little r, crossed with another big R, little r, we're going to end up with 1 out of 4 of them being big R, 2 out of 4 of them being big R, little r, 1 out of 4 of them being little r, little r. Sorry, I lost my voice a couple of days ago. Anywho, the question says, what is the expected frequency of orange spotted males? So in order to have an orange spotted male, they have to have the genotype of having at least one dominant Z. The other allele does not matter because whether it's dominant or the recessive Z allele, the orange allele is going to be expressed since we have at least one of them. And it also has to have one big R and the other allele does not matter because if it has one big R and one little r, for example, the big R is going to be dominant over the little r and it's going to produce no color, so the individual is going to turn out orange or whatever color that's impacted through the Z gene. So if we look at, for the orange spotted males, having at least one Z and the other allele not mattering, we have 2 individuals right here. Both of these males have at least one big Z. So if we add them together, we get 2 out of 4. So we get 2 out of 4, and we have to multiply that with the ratio of having one big R to any other allele. We have 2 different genotypes with at least one big R. If we add them together, those are 3 out of 4. So 2 out of 4 times 3 out of 4. That will give us 6 out of 16. And to find the frequency, you just divide 6 divided by 16. And that gives you 0.375, if my math is correct. To find the frequency of an orange spotted female, females only have one Z, so she has to have the genotype ZW. And at the R locus, the same deal, has to have at least one big R, and the other allele does not matter. Having ZW is a 1 out of 4 ratio, multiplied with big R, other allele not mattering, is 3 out of 4. And that gives us 3 out of 16. And that equals, in order to find the frequency, 3 divided by 16. If I'm not mistaken, that is 0.1875. I'm going to check my math on that. And that is correct. The expected frequency of a no-spotted male. In order to have a no-spotted male, you have to be homozygous recessive at both of the different genes. So we have to have a ZY, ZY, little r, little r. If you look at all the different genotypes we have for the F2, for the males, we have Z, 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 ZY. We have no ZY, ZY, which means that we have a 0. And little r's is 1 out of 4. So 0 times 1 out of 4 is simply 0. Now, the frequency of having no spotted females. In order to have a no spotted female, you have to have Z, Y, W, and little r. If you look at the different genotypes for the Z gene, we have ZYW, we have 1 out of 4 of them. Multiplied with having little r, which is 1 out of 4. And that gives us 1 out of 16, which equals 0.0625.